Mechanical engineering and biomedicine go hand in hand in the field of orthopedics. Implants, joint and bone replacements, and other mechanisms are being integrated into the human anatomy to restore and revitalize movement. Today we will be taking a look at the manufacturing of a cervical spine implant plate. Here is a photo of the original inspiration implant. Some key challenges when manufacturing orthopedic implants such as the one we will make today are achieving excellent dimensional tolerance so that the implant will sit properly on the bone, part strength and robustness for spinal support and longevity of the implant, and keeping time and material costs low so that patients have access to these affordable implants. This cervical spine implant is used to decompress and stabilize the spinal structure. Let's get started with the manufacturing process. First, we begin by making the CAD file for the implant in SolidWorks. In order to make the curvature of the implant fit with the cervical region of the spine, research was used to find cervical spinal radius of curvature, as well as dimensions such as plate diameter and height. The dimensions of the implant, 44 by 22 by 4 mm thickness, were determined using market research. Once the CAD file is finished, it is uploaded to Autodesk Fusion 360, a computer-aided manufacturing software. Make sure to put the stock dimensions into the software for reference. The machining process of a CNC mill is then designed and simulated in the CAM software. Next, we will prepare the stock by creating a flat surface on the workpiece top using a bandsaw. For implants, you would typically use titanium or a titanium alloy, but for demonstration purposes, we will be using aluminum today. Next is the setup of the CNC machine. Use parallels to install your workpiece properly into the clamp. Install any needed tools into the machine and calibrate them. Also, conduct a 4-point square calibration on the workpiece so that the CNC can determine where the center of the workpiece is. G-code is generated from the CAM simulations and uploaded to the CNC system, the Sinumeric 828. This G-code consists of coordinate points that tell the CNC exactly where to go throughout the machining process. The programmed CNC machining process has 9 distinctive stages. Number 1. A facing mill is used to shave the stock down to where the top of the part will be. Number 2. An end mill is used to cut out a 2D curved part outline. Number 3. A flat bottom end mill is used along with a feature called 3D Adaptive, which contours a rough blueprint for the 3D profile of the part. Number 4. An end mill is used to cut out the shape in the center. Number 5. A ball mill is used to refine the 3D contour shape of the part. The mill moves around the edges of the part profile. Number 6. A ball mill makes parallel runs back and forth across the top of the workpiece. This smooths out ridges and helps the top face merge smoothly into part sides. Number 7. Major and minor holes are bored using an end mill. For stage 8, the screw holes are identified using spot drilling. And for stage 9, the screw holes are drilled using peg drilling. Finishing off in the CNC, the screw holes are then tapped to create threads, and air is applied to remove metal residue. Here's the part right after being removed from the CNC. Today, we will only be creating 3D contours on the front of the spinal implant for demonstration purposes. This means that the back of the part will be flat, having no curvature. For this reason, we can use the bandsaw to remove the implant from the workpiece. After sanding and polishing, our part is finished. I hope after watching this machining demonstration, you now have a better understanding of how automated machining processes, such as CNC milling, can be used to produce parts like medical implants. Applying manufacturing engineering to biomedical fields such as orthopedics allows clinical providers to give more accurate and more affordable healthcare treatment.